And today I'm going to talk to you about the Jacobi algorithm, what it solves, how it solves this, and the applications of this algorithm. I always use some examples to convey key points, and we'll go through my own Python implementation at the end. And the lovely man on screen is Carl Gustav Jacob Jacobi, the creator of this wonderful algorithm. Firstly, what are we solving? We are solving systems of linear equations. A system of linear equations is a collection of two or more linear equations, believe it or not, involving the same variables. Here is a 3D example where each plane is a different variable and kind of represents our solution space of this variable. And then the dot in the middle is where we would aim to converge when we applied the Jacobi method, as this is our solution. Then we have the component representation, which is where we derive most of our formulas from, and the more mathematical standard. And then lastly, we have the matrix representation, which we can then take advantage of matrix operations. So we use this when we implement it with code. Looking more closely at the matrix representation, we can write many real problems in the form ax equals b, where a is the matrix of coefficients, so this would be the little number in front of x1, x2, x3. We have the vector of the variables, which is x, which will be what we aim to approximate, and then b being the vector of the results, so this would be the number after the equal sign in our system of linear equations. Unlike direct methods which provide exact solutions, such as Gaussian elimination, the Jacobi algorithm is an iterative solver which generates approximations for the solution vector within our specified tolerance. So it starts by having an initial guess, which we usually just zero out all of the x values in the x vector. Then for each equation, we compute the new values using only the values from the previous iteration, not the current one, which is where we differ from the Gauss-Seidel algorithm. And then we update the x vector with all of our new values. We check if this is within our convergence tolerance. If it's not, we keep going. Below you can see the update formula, which loosely translates to each variable being updated from the prior iteration. But it's important to note not all matrices are created equal, and some matrices do not converge with the Jacobi method. Therefore, we can check if a matrix meets the convergence criteria. The convergent criteria being diagonal dominance, which is the property of square matrices where each absolute value of the diagonal entry is greater than or equal to the sum of the absolute values of the rest of the row. Pretty catchy, right? So on the left we have matrix A, which is diagonally dominant. This is because all of the diagonal values are 3 or greater, and the rest of the row sums up to 3. Whereas matrix B isn't diagonally dominant because of the last row where we have a 0 and the rest of the row adds up to 3. Therefore, the Jacobi method will not converge for this specific matrix. Some applications. The Jacobi algorithm has many applications, but here are two examples. PageRank models incoming and outgoing links of web pages in a matrix. This is usually a sparse matrix due to the vast number of unrelated web pages on the World Wide Web, which leads into some of the efficiencies of the Jacobi algorithm. And then we can also use it in fluid dynamics to approach solving Navier-Stokes equations, which is essentially just solving large linear systems iteratively, and engineers can use this to simulate aircraft aerodynamics and weather patterns. Now I will walk you through my Python implementation. On the screen, you can see 3 test cases, one with 2 variables in our linear system, one with 3, and one where we did not have diagonal dominance within our matrix. Main is the main entry point where we define our test cases and we iterate through them and take out the various arrays. First, we do our convergence checks, and we check if A is a square matrix, we check if B and A have the same number of rows, otherwise we have an incomplete system, and we check for diagonal dominance within this. Then once that has all passed, we move on to the main Jacobi function where we initialize our x value with zeros and our x new with zeros, and then we loop for a number of maximum iterations or until we have converged here, and we apply the update formula to the matrix until we have reached our convergence tolerance or the maximum number of iterations.